All right, so now we're going to talk about rectilinear motion or straight line motion. Okay, so you kind of want to think of these as a number line, or you can think of them as a vertical number line if you're talking about altitude or anything like that. So most of these rules you might have learned in a physics class, but honestly, all the information should be able to be solved using calculus strategies and concepts, okay? So I'm just going to review all the rules at the beginning, and then we'll do some example problems. But this will be multiple choice questions, and it is almost always a free response question, one of the six. So you just want to know a lot of different concepts. We will revisit motion when we learn about integrals in January. So right now what you notice is that the position function, this is going to be the original. And so if you want to know where something is located or how far it moved, you would use the original function, okay? And usually we let that be s of t, but it can really be any letter that's denoted. We use t for time, so we don't use x as the variable typically because these are application problems. The derivative of position is the change in position, which is referred to as velocity. So v of t is, we usually change the names. If you don't want to write it with a v, sometimes they will write it as s prime, so just be flexible. So velocity is really the change in position, and they call that the instantaneous change, but it can be over an interval in time. And then the change in velocity is acceleration. So a of t or s double prime of t, okay? This is something that comes up occasionally, typically with physics students, but speed is known as the absolute value of velocity. So velocity, because we're talking about a change, it's directed speed. I like to think of it that way. So velocity can be positive or negative. Speed is the absolute value. Okay, so speed and velocity both give us information for how fast a function moves, but velocity, if it's negative, it indicates the direction of down or to the left. If it's positive, it means it moved up or to the right. Okay, and so you see here, if we're talking about velocity as negative, it means it moves left or down. If our velocity is 0, it means our object is stopped. So it might say, like, when did the car come to rest? So you would take the derivative, set it equal to 0, and solve it. Moving to the right or moving up is going to be when your velocity or derivative is positive. Okay? All right, another concept that might be discussed is total distance traveled. So this one is kind of tricky. They will usually give you an interval, and it's great if you just plug in those endpoints, but that only works if your function never changed directions or went from positive to negative on the derivative. So you always want to double check, okay? It's usually a trap. So what you want to do is you want to take your derivative, set it equal to 0 to find out when your particle is at rest because it probably changed directions. So then we want to substitute the rest times and the endpoints to find all of the positions and then add up those distances, okay? You might see the word displacement, and that means net distance. So if I move to the left, let's say I started at 0. If I move to the left 10 and then I move to the right 6, I have a displacement of 4, okay? If I want total distance, I would have moved 16. So see, I would have to add those together. So just know what the words mean because it could get tricky. All right, acceleration. This one is kind of a tricky concept to think about, but acceleration equal to 0. What does that really mean? It does not mean that the object has stopped. Remember, the object is at rest or stopped when the velocity or change in position is 0, okay? So an acceleration, think about your car. What instrument on your car might ensure that your vehicle has no acceleration? Well, cruise control. You press that button and I'm still moving, so I'm still changing distance. I'm not stopped, but I'm not speeding up and I'm not slowing down. Now, I know you can hit buttons to move up and down, but cruise control typically is when you stay at the same speed, the same change in position over time, constantly. Okay, so keep that in mind. So they might say accelerating left or down. Velocity is not changing. This is the word they could use, not position. And the object is accelerating right or accelerating up. That is not the same thing as speeding up, though. So please really pay attention to the words. If they want acceleration to be going to the right, you'll see that word acceleration. Okay, so the most missed question, even though I tell students this, it's just misunderstood, and it requires checking and comparing more than one thing. This is typically a free response question for like 1 or 2 points. So they will say speeding up. When is the particle speeding up? When is the particle slowing down? So these specific words are comparison. So if something is speeding up, it means that my velocity, which is your first derivative, and my acceleration have the same signs. So they're both positive or they're both negative. And people say, well, why does that mean I'm speeding up? Well, those forces are working together. So if I'm moving left and my acceleration is moving to the left, it's pushing me along. Think of it as the wind. So I'm already walking to the left and a wind comes and blows behind me to push me faster, I would speed up. Same thing to the right. If I'm walking to the right and a wind is also blowing me to the right, that will make me walk faster. That speeds me up. So same thing with slowing down. If you're walking to the left, but the wind is blowing to the right, it's holding me back and that slows me down. Those forces are opposite and they're working against each other. So your first derivative and your second derivative would have different signs. Okay, so just get that. I think logically when I'm standing in front of you and you can see me doing that, it makes sense. But for students just to think about like, oh, speeding up, that means my velocity or acceleration are positive. No, they could both be negative, and you have to check both. Okay. All right, that is 7.5 minutes of just all the rules that you might be tested on motion. Okay, so let's try some practice. And I have a ton of practice, so if you don't need all of these problems, please feel free to stop watching and try the homework. Okay, so for number 1, it just says find the velocity and acceleration of the particle, and they give us the position. So velocity, I'm just going to label it, is going to be x prime. You can change the letters if you want. And these are nice. This is a domain restriction. So if it's original domain restriction, this should make sense because time should be positive. So we get 3t squared minus 18t plus 24. And same thing, t is greater than 0. We just want you to get used to the relationships. Acceleration is our second derivative. These shouldn't be super tricky to do. Okay. And then we just wanted to do some trig kind of chain rules. So same thing, find velocity and acceleration. So I'm going to say velocity, well, this would be a chain rule. So remember, you do the derivative of sine is cosine. The inside stays the same, and then I have to multiply by the derivative of 2t, which is 2. I'm going to put it in front because I can. And then the derivative of cosine is negative sine. So I'm just going to even change that, and I'm going to write negative sine. Acceleration, well, same thing. The 2 stays. The derivative of cosine is negative, I'll write it here, negative sine. The inside stays the same, and then times the derivative of its inside, which is another 2, minus the derivative of sine is cosine. So if we clean that up, we'll multiply all of those together. So negative 4 sine of 2t minus cosine of t. So any function can be used, but these are typically not going to be quotient rules. They're going to be something kind of fast. If we want to solve, they'll probably do some exponential functions and some quotient rules because it helps you solve for them. So number 3, if the position of a particle is given by this, find when the particle is changing direction. So what I want to know is when I'm at rest, so I want to take the derivative and set it equal to 0. And then I really do want to check the signs to see that they change. So I'll show you how to do that. Sometimes they won't change. Most of the time they will though, but I could pick some functions, especially with piecewise. So if we take our derivative, I can't split that up, so you will have to do a quotient rule. So low d high minus high d low all over low squared. So if we distribute, we get 2t squared plus 18t minus t squared. And that simplifies to be just 1t squared. Okay, now I could do common factoring, but nothing's going to reduce, so this would be okay. And so what happens is we want to set that equal to 0 to find out where we might possibly change directions. Well, when you set that equal to 0, we would multiply by our denominator, which eliminates our denominator. I know as a domain restriction, t cannot equal -9 because that makes the original function not defined, but that's not in our domain restriction, so that's not relevant. So we would get t squared plus 18t equals 0. We're going to common factor. So t equals 0, t plus 18 equals 0. So subtract. But remember, because of our domain restriction, we don't have this. T equals 0 is actually not even defined. And so what does that mean? Well, if we solved it, these are the only possible times that our particle would change directions, and they're not possible based on our domain restriction that was given. So what that means is that the particle never changes directions. It's either always going to be moving to the left or it's always going to be moving to the right. Never changes. Now, this isn't the question, but let's say the question said, well, how is the particle moving? If this is our derivative, and I just simplified it, what we want to do is we want to substitute any value greater than 0 that we want. So I'm just going to plug in 1. So what if t equals 1? Well, I'd have 1 squared, which is positive, plus 18, which is positive, over that squared is always going to be a positive, so I'm always going to get a positive number. And it won't matter any other number I plug in that's greater than 0 because I know we don't ever change directions. So since my derivative is positive, what that means is our particle is always moving to the right or up. Okay, so they might ask you that question. All right, let's look at number 4. This one's definitely a nicer one, but number 3 was good because sometimes stuff like that happens. So if this is the position, well, I want to find the distance that the particle travels. So, and it's from t equals 2 to t equals 5. So what I'm going to do is I'm going to go ahead and find my position. And I've got t equals 2, and I know t equals 5. And so if I want my original position, I'm plugging it into the original equation. So I've got 2 squared plus 2 times 2 plus 4. So what's that? 12 plus 4 plus 4. So that's at 20 if we are on a number line. And then if I plug in 5, we get 5 squared is 25, so 75 plus 10 plus 4, 14. So we get 89. Okay, so I started at 20 and I went to 89. So we would have moved 69 units. But we want to make sure that we never change directions. So for change directions, we're going to take our derivative and set it equal to 0. So our derivative is 6t plus 2 and set equal to 0. Well, subtract 2, divide by 6. So at negative 1/3, it would change directions, but we don't have that because we're only going from 2 to 5. So now I do know that we actually moved 69 units. Okay? It's always good to check because you just never know. Oh, let's look at number 5. I bet you can tell what happens here. So we want to find the total distance. So same thing. I'm going to do position. We've got 0 and 6. If I plug in 0, I get 0. And if we plug in 6, what's that? 36 minus 48. So negative 12. Remember, you're on a number line, so we can have negative 12 as a position. We move to the left or we move down. So let's figure out if we did change directions. So if I take my derivative, so right now we would have moved 12 spaces to the left, but it doesn't matter. It's still 12 units. You don't say you moved negative 12, okay? If we add 8, divide by 2, that means we changed directions. Well, we were at rest at 4. So what I want to do is I want to plug in 4 to see if it's between 0 and negative 12, indicating I was moving to the left the whole time anyway, or not. So if I plug in 4, we get 16 minus 32, which is negative 16. So actually what happened, let's give you a visual. It's negative, but not how I was expecting. Is we started at 0, because that's what it says, and then we moved, after 4 seconds, we moved to negative 16. Okay? And then my particle from 4 to 6 seconds, it moved to negative 12. So I actually moved to the right. And that's not what I originally thought because I hadn't found any other information to contradict myself. So really, I moved 16 units here and we moved 4 units here. I want just the total distance that I moved. So we actually moved 20 total units. Okay, you see how that works? All right, number 6, here's my position. Find when the particle is changing directions. Okay, I'm going to have to use a calculator for this, so I'll use one on the internet. So I'm going to take my derivative, and I get 3t squared plus, you would have a graphing calculator, 16t minus 2. And I want to know when that's equal to 0. Okay, so I'm going to actually just use Desmos because I don't have, I might have this available. Let's see if my Smart View is going to work. I have 39 days, so I'll just continue. All right, and it should open in a second. Okay, so we're going to go to y equals, and we'll go ahead and just clear all of this out. Oh, it lets me. There we go. There we go. All right, so we're going to type in our function, which was 3x squared. Use the x, so 3x squared plus 16x. 3x squared plus 16x. So 3x squared plus 16x minus 2. And we're going to graph it. Let me double check to make sure that was right. Yep. So we want to know where it equals 0. So we had, I'm going to draw a picture here so we know what we're doing. So, all right. So we're looking at, I've already forgot, over there and over there. Okay, it's really close. So when it equals 0, we're looking for this value and this value. It does say t is greater than 0, so this is irrelevant because x would be negative, irrelevant. Okay, so I need to find this. So on your graphing calculator, we're going to go ahead and do that calc button. So blue, calc, and we want 0. So I'm going to type in 2. Okay, and now it should say left bound. So you want to move your cursor. This is where we think it crosses. You move your cursor to the left of where you think the answer is. You hit enter. Then it's going to say right bound. So we're going to move our cursor to the right of where we think the answer is. And you don't have to be super exact. You're just giving it a window to find. Then it's going to say guess. So now I just move my cursor where I think it is, as close as it'll go. It doesn't matter. And you hit enter again. It's going to tell you. In the AP, it's 3 decimal minimum. So I would write 0.122. Okay. And so that's it. So you have to be able to find roots on a calculator. All right, my last question I'm going to make smaller because it's got like 6 parts. So the first thing you want to notice is this is a little tricky, but this is a graph of the velocity. So I always make a little note that this is a derivative graph. Okay. And we're going from 0 to 9 seconds. We've got this little chart, and I've got numbers on the axis. So at t equals 4, is the particle moving to the right or the left? So remember, we want to know if the derivative is to the right, positive, or the left means the derivative is negative. So I go to 4, and this is the value. So remember, this is the derivative graph, and so I know the derivative value is positive, so that means we're moving to the right. So I would say that v of 4 is greater than 0. Okay, and that would be enough for an explanation. On part B, it says, over what time interval is the particle moving to the left? So same idea. If we're moving to the left, we want the derivative to be negative, and that's the graph of the derivative. So I want to know, where are my negative values? Well, here's negative values plotted. So that starts at 1, 2, 3, 4, 5, and continues. At 5, it's 0, so we don't include it. Oh, and to 9. So I could say from 5 to 9, since it's an interval, sorry, because it didn't stop. Or you could say 5 is less than t is less than 9. All right, part C. At 4 seconds, is the acceleration of the particle positive or negative? So remember, acceleration is the derivative or the slope of velocity. So since this is velocity, I want to know what the slope is. So at 4, this would be my tangent line, and that has a slope that's negative. Does that make sense? So since the slope of the velocity is negative, well, that's acceleration because it's the slope of derivative of velocity. We're going to say negative because v prime of 4 is less than 0. That's the notation. You can write it out in words. Okay, we're going to make this smaller because I got to be able to see the graph for part D. So on part D, it says, at what time in a given interval is the particle farthest to the right? So we have to think, how is this moving? So when it's above, our velocity is positive. That meant we were moving to the right. So that's up until 5. So we're going to the right. And then our derivative is negative, so then we go to the left. So I go to the right, and then I go to the left. So it says, when am I the farthest to the right? Well, I'm the farthest to the right at 5. Part E, at t equals 4, is the particle speeding up or slowing down? So I need to compare the velocity and the acceleration. So at t equals 4, the velocity, which is what's graphed, is positive, or greater than 0, however you want to write it. And the acceleration at 4, or velocity prime, was negative. So negative. So since we have opposite signs, we would be slowing down. And my explanation is my signs. All right, and then F says at t equals 5.5 is the particle speeding up, slowing down, or negative. So let's look at our graph. Here's 5.5, which is about right here. Well, my velocity of 5.5, well, it's below x, which means it's negative. And my velocity prime, which is my slope of my tangent line. So my tangent line also has a negative slope. So we're going to say we are speeding up. And my explanation is those signs. At t equals 7, so here's 5, 6, 7, so I'm talking about right here. My velocity of 7 is negative. And my acceleration, or velocity prime, of 7 is 0. Well, 0 doesn't have any signs, so we're going to say neither. Okay, all right, I know this was a lot of notes. Motion is pretty important. I just wanted to put it all together in one section, so go ahead and give it a try.